Okay, this is going to be a recorded session. So let me restart this one. Okay, I think it's okay. Okay, let me share the screen with you. All right, I'll just go through the your assignment 1. Okay, the due date of your assignment 1. I think let me double check the due date. Let me see here. Tutorial 1. The due date for assignment 1 is February 11th. So another 1 week. Another 1 week time you need to submit your assignment number 1. Assignment number 2 due date is going to be March, the end of March. There's some time away. So we need to arrange for our lab session. Okay. Most likely it's going to be on the after just at the end of Chinese New Year. We're going to do that, the lab session. But for now, I'll focus on your assignment number 1. So if you look at the question 1A, okay, question 1A, you're given as the voltage in the function of time and the current in the function of time. Okay, we have this exponential function and this is a ddt. You need to take the derivative of the voltage function. So the first question, the first part is asked for the current IT. So this is the one you asked for. So you need to do the differentiation of this dt. Okay, do this derivative. You just substitute the vt into here and then do the derivative. Just like what we have discussed. Okay, you do this, and then you will get the answer in somewhere look like this. All right. Part 2 is to find the total charge between time 0 to 1. So this looks like we need some kind of integration to compute the total charge from 0 to 1 second. So our approach is going to because based on the physics, the charge actually we can use the charge. The total charge is use the current and do the integration. Because the current is the flow of the charge, so you use the current function. So the current function from part 1. So you need to obtain these answers in order to continue to part 2. So you do the integration of this function here, it, from 0 to 1, and then you'll get an answer in column. The unit is in column, COU, LOMB. Okay, so this is quite straightforward. Part 3, calculate the power. So for the power, we use the normal power equation, which is the voltage multiplied by the current. But in this time, we need to take the voltage as a function of time and current as a function of time. From here, VIT and the VT. Okay, we take these two, and then we multiply them together. We will get the answer in unit watt. Okay. You also will find that your answer doesn't have some exponential value also. Something multiplied by exponential something, okay? So your answer is going to look like this. And then for the part B, all right, I continue to part B. For the part B, you're going to have first explain the Ohm's law. You look at the total marks is 5. Therefore, you can use the words. I mean, use English words to explain it. So if you can, if there is any equation, you may need to include the equation. If there's a diagram or anything can help to explain it, it's better to include the diagram also. In order to get the full marks, okay, you need to explain it as complete as possible. Second, by using the Ohm's law to find the current I, Okay, so for this question, let me see whether I've already discussed or not. Yeah, I already discussed before. So the current I actually is referred to this current I1. Current I1 here, this current I. So this is pretty straightforward. If you understand the basic circuit, you immediately can tell how to calculate this current I. Okay, you don't need any complicated steps to calculate the I1. The answer is just one step. You can get the answer. Okay, one step you can get the answer just like that. Right, and then number 3, by using the voltage division rules, find the V out. So what I can tell you is that the V out actually, the V out is actually the voltage across 3 kilo ohm. Why I say that? Because they are sharing the same nodes. This node and this node shared by the V out is exactly the same. So you can say V out is actually the voltage across 3k ohm, the voltage across from here to here. So here, if we think this one is by looking at this symbol, the minus is here. Okay, I don't know if they do it purposely or what. Okay, usually when you say, but it's everything you can do in the circuit actually. Everything you can do in the circuit, even though the current is flow from the here to here. From the second analysis, current is flow from the positive to negative. But if you indicate the current flowing in this direction, then your answer may be in the negative. Okay, and then the result is the answer may be in the negative because the current flow actually is actually opposite the actual current flow. You know what? Why I want to mention this one is that in the circuit analysis, we can define the current flow in any direction. For example, let me give you another example, quick example here. Let's say, okay, let's say you now and try to analyze a circuit. Okay, initially you don't know what happened, and then let's say there's a current flow through this resistor. So initially you have to assume the current is flowing from this direction, and then you call this current as I1, for example, I2, for example. And at the end, after some calculation, you found out that the current actually is the minus, let's say minus 2 ampere. So what it means, 2 ampere is the magnitude. 2 ampere is the magnitude of the current. How strong the current is, 2 ampere. Then this negative sign tells you that your current actually is opposite. Your actual I2 is opposite here because it's a minus. Means the current you define like this actually should be like this. So if you follow I3 here, I3 should be equal to 2 ampere like this. Because if the current is flowing in the right direction, you should get the positive number. If you define the current and then you get a negative number, then it tells that the current is in the other direction. Okay, so this doesn't matter actually. When you get a negative number, it tells you that the assumption is opposite. Okay, but you still get the correct answer 2 ampere. You just tell you the answer, the direction is opposite. Okay, so the question assume that the current is flow from the top to bottom here. So the top is negative here. So the negative here is negative 6 volt. So whatever answer you get, it only indicates the direction of the current flow. Okay, so this is not a big deal actually. Well, but what I can tell you, the answer is negative also. Well, what I can tell you, the answer for the part 1, I need to give you some direction also sometime. For the part 1, just to explain it, just like here, explain it. Part 2, I can give you the some hints right now. Okay. Part 2, the your answer for the I1 is actually minus something milliampere. Okay, so you need to find out what it is. Okay, find out what is this. I can assure you the answer is minus. Also, if you observe the circuit, this node is close to the negative, so it's to be minus, and then the magnitude is a 6 volt. The potential energy here is 6 volt, and then this node is near the negative end, near the negative terminal. So this node, same as this node, is 6 volt. Okay, so from there you can tell answer is negative. You can tell answer is negative from the observation. Okay, and then the part 3, find the voltage division. So I already showed you previously. This is voltage division. So what we mean is, let's say you have 10 volt here, and then let's pick a good number here. Let's say you have 8k on here, and then you have a 2k on here. So you know that the 10 volt going to be shared by these two, right? So the 8k will share 8 volt. This is how the thing works, right? 8k will share the 8 volt. Another 2 volt goes to the 2k on here. Measure from this node to this node. So this node is 0, right? 0. So after, from another point of view, another perspective, 10 volt, starting 10 volt. After 8 volt, initially here's 10 volt, right? Here's near the 10 volt, of course. And then after the 8 volt, here is become 2 volt already. I mean the potential at this node is 2 volt. And then another 2k is gone. And if you measure the potential here is 2 volt, or you measure the node here is 2 volt. Okay, but if you understand the logic behind we call the voltage division, 10 volt divided by 8 and 2, the ratio of 8 and 2. Okay, so if you refer back to this circuit again, probably you can tell how the voltage being divided. Even though here is a very simple, down to earth, simple, right? Just two components only. But here we have 3 components, 1, 2, 3. But it's still simple. If you look closely, it's still the voltage division rules still apply to this circuit. Okay. So you need to figure out what is the V out. What is the V out? It's quite straightforward actually. Because if you understand these rules here, this node. So the node is very important. Okay, I can give you another thing. The node is very important. Node 1, right? This is node number 2. Node number 2. So node 1 is 10 volt. Node number 2 is 2 volt. Okay, from here we can guess the node here, the node here, the node here. Okay, this is for part 3. And then this one we already discussed about it last time. I gave you one example also. To figure out the which one is supplying power, which one is dissipating the power, ABC, we have 3 unknown. We have 3 unknown elements, ABC. We need to figure out which one is supplying, which one is absorbing the power. So this is the measurement we have for these 3 elements, and then the current flow. So this current flow 25 amp is flowing through these 3. They are connected in a loop. Okay, in one loop, right? So this 25A flow through A, flow through C, and flow through A. Okay, this 25 ampere. So you need to determine the which one's supplying, which one's dissipating, and also calculate the power dissipation. Remember, I already showed you how to answer it last time. Right here, right? You need to determine which is which, right? I give you both options here. And then the 3, you need to calculate the power. Okay, now at question number 2. Okay, now at question number 2 here. Let me see this one with this. All right, this one. Wait a minute. It's not the same, right? How come I give you this one? Okay, okay. Oh, this one is a 2B, 2B, okay, 2B, 2B. Okay, let's talk about 2A. Let's talk about 2A. Question 2A is look a bit complicated, of course, okay? Let me see. It looks a bit complicated because we have the dependent source here. So this voltage, actually this is the current source. Don't be confused by this Vx. V is a voltage, right? But the value here is the 0.5 IB, and then this is the arrow. Arrow means is the current. Only positive and negative is the voltage. Okay, so this is the current source. Okay, but current source also can have a voltage across. Okay, so this current source is depend on this current. Let's say you have 4 amp flowing through here, then you have a 2 amp here, because this is half of the IB. I mean, whatever IB flowing through here, let's say 4 ampere, you get 2 ampere here. So this current source is depend on this current. You get the meaning about. This is a power supply. This power supply, after this resistor, you actually, after all these components, the power supply was supplied certain ampere, and then this ampere will determine this current source. This is another source, just like the voltage source. This is another source, but this current source is depend on this current. Okay, actually in the electronic circuit, we can have situation like this. It's quite common actually. We have 2 voltage source, 1 current source. This current source is depend on this current ID. Okay, so from this circuit, suddenly we have a dependent source here. This is dependent. Another opposite is called the independent. Independent is like this. Independent is a 4V and 12V, 4 volt and 12 volt. They do not depend on anything, right? They just supply 12 volt and 4 volt. So they call the independent source. So this one is called the dependent. We depend on this. Okay. So by understanding this, let's read the question. Find the voltage Vx across the dependent source by using the Kirchhoff law. So Kirchhoff law, we have a Kirchhoff's current law and the voltage law, and also the Ohm's law. Using these three to find the Vx. Vx is unknown right now. So what the given is the current IB is not given, only given the component value, the source value, and the component value. So it looks like you need to determine the IB. After that, the part 2, you need to find the power absorbed or supplied by the 4 volt. So you need to calculate the power absorbed or supplied by the 4 volt. Okay, so you think about this. You think about this when I come back later on after the break. I will show you some guideline, at least some guideline how to go about doing this. So before I go, I just need to copy this. Let me copy this before I go for a quick break. Then you think about this. Okay, when I come back later on, I will show you how to do this. But you better don't wait for my tips. Okay, try to figure out yourself first. Even though you make a mistake, it's how we learn, right? We learn from mistakes. So if you make a mistake, you're making a wrong assumption or wrong. You start with the wrong foot. Okay. Then you'll learn in the next time. You'll learn for a very long time. Okay. So if you just try to watch and read and try to learn, is not very efficient. The most efficient way to learn is by making mistakes. So you make some assumption, then you make some mistake, then you learn from the mistake. Okay, so I will walk away for a while. Okay, I will come back. I want to focus on this one. And let's see. Today we have. Let's see. Today, let me see. We have how many sessions? How many tutorials we do we have right now? Let me see here. So I want to ensure that I can cover all in So we have, after today, the next one is a March 3rd of March, right? But the due date is the February 11, right? I remember. The due date, where is it? Yeah. So due date, looks like today I need to complete off, okay? Otherwise you will, because the next time we meet is the 3rd of March. T3, let's call it T3. T3 is on the 3rd of March. So I think to make sure that we can fulfill this requirement. Okay. So before I go, I want to take a look at the remaining question. So this one is easy. This one is quite okay. This is quite challenging. Also this one. So question number 3 is quite challenging. Question number 4 also. This 2 is not. This one you can say is easy. This one. Just follow the steps. Follow some steps. This one, you need to understand the Norton. This one is quite challenging. I should say this 1, 2, and 3 is quite challenging. Okay, probably you are not able to get 3 marks. So we try our best. Okay. So we cover this, and then for the remaining time until 5:30 until 8:30, right? 5:30 until 8. 5:30 until 8. Now we have what? Until 8. Now we have, it's 2.5 hours. Yes, 2.5 hours session. I thought it's 2 hours. Now we have 2 hours left. So let's take a break now, then I will look at this one. Okay. I'll give some I'll help about 30 to 50%. Okay. So right now you try to figure out where should you start from here. So the question say, he didn't say using any methods, right? He said just say using Kirchhoff's voltage law. Okay. Looks like we need to apply both. Looks like we need to apply both KCL and KVL under the Kirchhoff's law. Okay. Let's take a break now. Let me make sure the photo is on. Mine is on. Okay, let's continue. So I'm going to help you here. First, you need to use a KCL. The first step is applying KCL. Okay, KCL at this node. This is called node A. At node A. Okay. Apply the KCL. Let me give an idea. KCL is the current law, right? So we have one current here. So this current is 0.5B. Another current here with no name. Okay, let's just call this one I, big I. Another current coming from here is called IB. Okay, so we have three current now. IB also, but this is half IB. This is another I. So you use this one to find the current. This I can be calculated, right? Okay. What I can tell you is that after you use a KCL, you get this equation. Okay. Then this is going to be your first equation. You still unable to find anything from this equation yet. You still there's some unknown here. IB is going to be your because this I is based on IB, right? So you can just put I at one side, I equal to something IB, right? You can just put this one to the other side. Okay, you put this I at one side, the rest to the other side. Okay, for example, the answer is going to look like this: something minus something. Okay, so this is going to be your first equation. You need the second equation using the KVL. Okay, so this KVL is around the root number 1. Let's define the root number 1 here. The root 1 using the KVL. So you sum all the voltages here. You sum all the voltages, you equal to 0. Sum all the voltages, okay, equal to 0, 1, 2, 3, along this loop. So this is going to be your second equation. Okay. After that, you still can't when you go through the step number 2, KVL. After you sum all the voltages, okay, you will be able to determine the IB. You will find the IB equal to something. Okay, from the KVL you'll find the IB. Then you use this IB, replace into the number 1, you get the I. Okay. After you calculate IB, then you can calculate the I equal to what? Because this I is based on IB. This I is based on these two IB. After you can find the IB from the KVL, then you can use this IB to determine the I in the first equation. Okay. Then you are almost pretty much covered already. So you need the last equation. KVL at loop number 2, loop 1. This is the loop 2. KVL at loop number 2 here is to sum all the voltages in this loop. We call loop 2. This is the loop 1. After you've done that, sum all the voltages equal to 0. Okay, going to be your third equation. After you've done this one, you'll be able to find the voltage Vx. Okay, so from here, after you find the voltage Vx is the part 1. So you continue to second part. You continue the second part. All the while here, we are doing the part 1 only. All the while here, we are only doing the part 1. Okay, part 1 here. So part 1 is to find the Vx only. So from here, you find IB first, then you find I, then you find the Vx. Then you complete part 1 only. Okay, now let's continue the part 2. Part 2 is to calculate the voltage absorbed or the supply by the 4 volt. So the 4 volt is here. Okay. So what I can tell you is this 4 volt. Okay, this 4 volt is also based on the current IB. This is the important tips. Okay, this is the important hints here. The 4 volt, the power of the 4 volt power supply is the you can use the V times I, right? V times I. I can tell you the I is actually this. This is the current flow through the form. So, okay, I think I give you enough information already. So the part 2 is straightforward. Only one line, you can find the answer. Okay. One line, you can find the answer. And then the part B, I think, let me see. I haven't discussed about part B yet. So part B is actually the find the equivalent circuit. Let me see the original. So find the RB from this network. Okay, this is part B. So this one is easy because, as you know, when you have two resistors in series, for example, like this. Let's say 1K and 2K. So the R, let's say you have a AB here, A and B terminal. So the RAB of the total equivalent resistance is equal to 1 plus 2 equal to 3K. Okay, 3K ohm, right? 3K ohm. So if we have, let's say you have a 1K, another 2K here, they are actually parallel. Parallel means they share a common node. This node is the same. This node share with this node, but this node does not share with this node, right? They are just across. This node does not share with this node. So we have 3 nodes here. We have 3 nodes here, 2 components. That's why it's a series. This one is called a series. So we have the 2 components, but only share 2 nodes only. Let's call this A. This call this B. B node. This node is same with this node. This node same with this node. Just a wire only. Unlike this one, we have 3 nodes. This one has 2 nodes. 1K, 2K. So the RAB total equivalent resistance for these two is equal to 1 over RAB equal to 1 over 1K plus 1 over 2K. This using a reciprocal value, or the quick way to calculate the 2 components is like this. The easiest way I use often is by using the multiply 1K on the top, multiply 1K by 2K on the top, and then at the bottom is the 1K plus 2K. This is the easiest way. Okay? So you go through this one, you simplify it until you find the last RAB. Wait, so you start first. You look at here. Okay. Hey, wait a minute. This is simple. This is the correct one, right? Okay. Okay, what you need to do first is to 4K is here, is to convert this one you see here, is to convert this one, the internal, you can see the T network, 2K, 6K, 12K here. Okay. What you can see here, the 2K, $12K, and the 6K, they form a network we call you can call the T network T network, or actually we call it Y network. Y network. If you can convert this one to the delta network, delta network looks like this. Convert from T to convert from Y to delta. So this one looks like delta, right? Those are the inverse delta. Delta is this one, like this right, delta. So this is the inverse delta. So from this one, Y to delta, you can go online and look for the formula. If you go to online, you type convert Y to, sometimes they call WYE, Y to delta. And then your search for some formula here. The RA, RB, R1, R2, R3. RA here, if you want to convert from here to here, RA is equal to R1 times R2, R2 times R3, and then at the bottom here you put R1. If you want to convert from here to here, you need to use this formula. If you want to convert from here to here, you need to use this formula. Okay. So after you because this is quite a common technique we use. Convert from Y to delta, from delta to Y. So in this case, in the center here is looks like Y. 1, 2, 3, right? Connected by center node here. 1, 2, 3. If you can convert, then the circuit will look much simpler. It will help you to reduce the circuit complexity. After you convert it, the circuit will look much simple. Then you can apply the normal technique to reduce it, okay, step by step, until you reach the last one. The last one only has one resistor. That will be your answer. Okay, so the next question here is part C. Okay, part C. Question 2C. 9 marks. Let's put it here. This is the next question. Okay, I give you some time for you to look at this one. When I come back here, I'm going to show you some guideline how to do this. Okay, just take a look at this circuit for a moment. Okay, I'll come back in a short while. Then we have how many questions to go? We have question 3 and question 4. I try to get it done within the next one and a half hour. Okay, but right now let's look at this question first. Okay, I only can give you about 50% of the guideline. If I turn this off, probably later forgot to turn it on. Okay, so better than cut this one. Okay, I'll come back later on. I can make a short one. All right, for this question, it said that it said very clearly that using the mass analysis. Okay, so you know mass analysis is doing the KVL. Okay, let me give you some background information. What we mean mass analysis is mass is actually you need to use the KVL. Okay, using the KVL to find the current. Okay, this is called mass analysis. The nodal analysis is the opposite, is using KCL to find voltage. Okay, this one is using the KVL to find current. So the first step, you need to do the loop number 1. We call this loop. Okay, loop 1. Loop I1. You're using the KVL. Using KVL, you will find one equation based on the I1 and I2. Give you some more tips. Okay, for the first equation you find, this one's easy, right? But you have this resistor in between these two loops, this resistor between the I1 and I2. So I can tell you that one of the voltages, some of the voltages, right? One of the voltages is 10 times I1 minus I2. Okay. So if you consider the I1 is in this direction, I2 is the opposite direction. Because I2 is the from I1 point of view, I2 is going up, I1 is going down. Okay, I1 is going down, I2 is going up. So I2 is minus, I1 minus I2 times 10. We need to find the difference between this, because this resistance is between these two currents. So we need to find the difference. The difference is going to be, we presume that the I1 is larger than I2. So the I1 minus I2. Part of it is the current. We assume the current is going down, right? I2 current is going up. That's why I2 is negative. Okay, let's take this one first. So the I1 is going down, I2 is going up, so this is negative. So this one is all equal to 0. You sum all the voltages equal to 0. So this one will be your first equation, consists of I1 and I2. Since we have two unknowns, we need to have two equations to solve the unknown, right? This is the basic mathematics. So of course we need to do another loop around the I2 using the KVL, because KVL is based on the mass using the KVL. So if we find another equation around loop 2, okay, around loop 2, and then what we get is at loop 2 you'll find the I2. You'll find the I2 equal to something, okay? After you've done the loop 2, this is the loop 1, you'll find I2. Then with I2 you substitute in, you'll find I1. That's it. That is the question asked for, is to find I1 and I2. Okay, that's it. That means you just need to do the two loop on it. Simple, I think quite straightforward. I don't want to talk more, I talk more probably confuse you, okay? Because it's quite simple. Okay, the next question. Question 3. Now question 3, you need to use the nodal analysis. This is opposite of mass analysis. So for question 3, okay, look at the circuit here. Q3 A. The nodal analysis. Just now the mass analysis, remember, nodal analysis would be using KCL to find voltages, as opposed to mass. Mass is a KVL to find current. This is the Kirchhoff current law to find voltages. Okay, so we need to find the voltages I1, I'm sorry, V1, V2, and V3. Okay, also this unknown also. So the rest also can be treated as a unknown also. But the main thing we try to find actually the node voltages is referred to V1, V2, and V3 using the nodal analysis. Okay, so this question is quite challenging. You need a full A4 page to solve this question. Okay, so let me give you some quick start first. Okay, V3 can be tell immediately. I cannot tell you the answer. V3 can be obtained from this circuit immediately. You don't need any calculation. And then the next one you want to do is a V1. V1 also can be tell immediately, but V1 still have some unknown. Okay, now after you have some clue about V3 and V1. Okay, let's write the first KCL. The first KCL at node 1. KCL at V1 and not V1. Yeah. You know KCL, right? KCL is sum of the current around this node. Previously, is the sum of the voltages in the loop. This is sum all the voltages 1, 2, 3 in the loop. This one is a sum all the current 1. Since it's pointing this one, it's pointing this direction, so we treat it as pointing downward, right? So we follow the path. 1, 2, 3, okay? At this node. Sum all the current here. And then after you've done this, you will get one equation. You will get one equation, something minus something plus, it could be positive if you bring over there, okay? Plus something equal to minus something, okay? But all this can be a bit different, because if you bring this one over there, it becomes positive, okay? If you bring this part over there, it will become positive. If you bring this positive over there, it becomes negative. So I just give you some idea. It looks like this. So inside this equation, you have V1 and V2. You have V1 and V2. So you have two unknown here. V1 is not so straightforward, right? Because this is unknown here. IY, you don't know what's IY, right? V2 is still unknown, right? So it is unknown here. So at least we have two unknown. For the time being, at least we have two unknown based on this equation. Let's call this equation number 1. This is equation number 1. Of course, we need to have another equation. Okay, so let's okay, let's do another. Wait a minute. Let me see. IY let's see here. All right, so we have another equation here. This is equation. Actually, this is equation number 1. Actually, this is equation number. Let's call number 2. This is equation number 1. Number 2. Okay. So now, after this step, probably you need to substitute equation. Substitute equation 2. Okay, in this case 1. Okay, substitute equation 1 into 2. V1 into something like that. So you will get the next equation. Okay, wait a minute, let's get confused here. Equation 1 into 2. Okay, then again, this is quite complicated. You substitute 1 into 2, then you substitute, wait a minute, let's see. After you've done this, V1, KVL, you get equation number 1. Wait a minute, let me see. I1. Oh, here I1. Okay, let's clear the confusion here. Remember, I tell you that the V1 also contain IY, right? The V1 node here, the equation contain IY. Okay, it contains IY. Okay, V1 contain IY. Now let's define what is IY, because this is the IY in this 4 times IY for this water source, right? For this dependent water source, right? It depend on this, right? You don't, it depend on this IY. So let's define this IY here. So this IY is between V1 and V2, right? I think for this part I can help you. IY can be defined as the voltage divided by the resistance. So the voltage is between here and here. The different voltage is different. So IY can be defined as V1 minus V2 over 2. So we have another equation here. Let's say equation 1, equation 2, equation 3. Okay, so you have 3 equations already now. Okay, let's substitute the equation into number 2. You substitute this equation. Now you substitute 1 into 2. Okay, substitute 1 into 2 here. Let's copy this. Substitute 1 into 2. So 1 is this. Okay, so we substitute this equation. Wait a minute. Let me get the thing like this. We substitute 3. Substitute 3 into 2. Okay, into 2 into here. V1. Okay, let me take the answer now, okay? This one is the 4 times I1. Substitute 3. Now you get the idea, right? 3 is IY equal to something, right? And then V1 is 4 IY, right? Substitute 3 into 2. You'll get another equation, okay? You'll get equation number 4. Okay, then with equation 1 and 4, you can calculate the V1 and V2. And then the last step you need to do yourself. Then calculate or determine the V1 and V2 using equation 4 and 1. Because equation 1 contains V1, V2. Equation 4 also contains V1, V2. Equation 4 you have minus something plus something, minus something V1 plus something V2. Equation number 4, right? Equation number 3, equation number 1, you have minus something V1 minus something V2. Okay. Then with two equations and two unknowns, you should be able to calculate the value. Create an equation 1. Calculate V1, V2. Then this will be your answer. Your answer is to determine the voltage V1, V2, and V3. V3 is already determined right away. So this is the part 1. So part 2, find the power. Okay, part 2. So I let you complete the remaining step. So at the end, V1 equal to what? V2 equal to what? And V3 equal to what? Okay, this will be your final answer for part 1. Okay, for part 2, the power actually, okay, for part 2, is it the part 2 or part 2? Part 2, right? For part 2, find the power of 4. This one is also not so straightforward. Okay, this one you need to use the KCL. You need to use the KCL at node 1, not V1. Okay, where is it? This again, right? Let me see this again. KCL and node 1. KCL and node 1. I think it should refer to a different node here. I think it should be KCL and node 2, I think they make a mistake. IY, actually KCL and node 1. And as for this one, I make a mistake here because the mistake they made in the answer script. This one, this is a mistake. Okay, this one should be V2. Should be here. You use a KVL here. You determine the V1, V2, V2, V3, V2 to ground. So we have the voltage across here is a V1 minus V2. The voltage across here is a V2, V3. The voltage across here is a V2 to V2. So here's a one current. We presume the current flowing down. We presume the current flowing this way. Another current is let's say we presume it flowing this way. Okay, let's see. Actually, based on the assumption here, let me give you a better one. Based on the assumption by this answer script, the three current actually flowing in the same direction. So let me do not to confuse you. Based on the answer script here, the current actually flowing into the same node. IY into here, this one into here, and this one into here. Okay. All into the same node. I mean, all current flow into the node. All current entering the node, not existing the node. Okay. Let's say you have this current, right? So it becomes IY I1 plus I2 plus I3 equal to 0, all plus, because all into the node. Okay, into this node, and into this node. The three arrow pointing to the node, so it's all plus. Okay. So like this case, this one in, this one out, this one out. In is equal to 2 out. 1 in equal to 2 out, or 2 out equal to 1 in, right? Equal to 0. Or you can say this one plus minus equal to 0, or plus minus this one equal to 0. Whatever you say should be correct, right? You get what I mean here. Let's say A plus B minus C equal to 0, right? You also can say C equal to A plus B, right? Also, you can say A equal to C minus B, right? So whatever you say is correct, you see. So what I mean is here, in, out, out. You can say this one equal to this two, or this two equal to this one, or sum of this all equal to 0. Sum of all equal to 0. Okay, so same in this case. But based on my answer script here, is assume the current all point into the node. Okay. So let's this is the node 2. So I make my correction just now. This actually should be 2, not 2 here. So when you try to find the IY, the 4IY, because part 2 is 4IY. The part 2 4IY, you need to use a KCL and node 1. Okay, and node 1. Okay. Let me give some guideline. It's something like, let's see, we have an I, right? With the I, with the IY, we have the 2Vx, right? We have IY, 2Vx into this node V1. So the equation should start with the I at least plus something minus something equal to 0. Okay, I give you the first one, I give you the last one, so you figure out the in between. So after you figure this one, okay, and then you kind of expand it, because this one can be expanded into something like V1 minus V2, V2 minus V1 over the resistance, right? Because this one is a current, right? This one is a current, for example. For example, let's say you talk about this 2 ohm here. Let's say you talk about 2 ohm. Let's say this current, let's say I don't want to talk so clear. Let's say you have one resistance called 2 ohm here. This 2 ohm, at least it has 2 terminal, one here, one there, right? Let's say you have voltage here, voltage here. So in order to determine the current flow through the 2 ohm, let's call this current is I2 ohm, right? You can use ohms law, right? I2 ohm equal to V over R, right? So the V is not this V, not this V, right? The V is a V, total V. It's a V1 minus V2. It's the total voltage across the, it's the voltage difference between these two nodes. It's the voltage difference between these two nodes, okay? It's called this V here. You cannot just take one of these, you cannot do that, okay? You take this one is not enough, that's enough. You need to find the total. What is the total potential energy need to handle by this 2 ohm? Okay, not this one, not this one. You need to take 2 points to find the real potential, right? For example, let me give one example. Let's say this is the water, right? Let's say you submit, you are under the water. Then your body has some pressure, right? Your body has some pressure, and then the water level pressure, right? And then the pressure here. You need to have a difference. You cannot just take the pressure inside your body. You can determine your current pressure, right? You need to determine the depth of your water, the total depth here. Then you also need to calculate the pressure at the surface, the pressure inside your body. To calculate what is the current total pressure, right, inside your body, the total pressure that you need to handle. Just like this one also, you cannot just take this voltage and this voltage alone. You need to take both to measure the voltage suffered by this 2 ohm. So this one must be V1 minus V2 divided by 2, right? So you expand this one just like that for these two current. After that, you should be able to find the I. At the end, you can find the I. I is very important, okay? And then the power actually is something multiplied by the I. Is the last answer in what? The power is something multiplied by the I. You can tell very clearly, right? The power of the 4IY, because the current I flow through it, then the I must be there. I times the V is the power. Power it can come in three forms. Okay, power equation. It can come in three forms. Okay, three forms. It's either V over R. Let's pick the one. Let's pick this one. Okay, it's either I times V square over R or I square times R. Power. Three form. If you have V and I, then you just multiply to get the answer. If you have V and R, you just do this. If you have R and I, you just do this equation. So we have three forms to calculate the power. If you come back to this question again, so this power, one is the I, the other one cannot be R, right? This one cannot be R, right? This one is given the power of 4IY. So what is 4IY? So the answer is very clear already. Answer is very clear. I, what's the other one? Okay, so I leave it to you to think about it. Okay, and then for the next question, I want you to take a look first, then I'll come back to discuss. The next one, 3B is here, and then we have two remaining questions. Okay, I think we can make it by 8 p.m. we can solve these three. I think. Okay, so for a moment you just take a look at this. The next question. Take a look at this question. 3B. Maybe. Okay, let's say this one. Oh, I think I will override the previous one. Just save it as P2. Okay, take a moment to study this circuit. So come back that for a while. And then I'll show you how to solve this one. You need about two A4 pages to solve this 3B. It's not so straightforward. You need to figure out at least two equations. All right, let's come back to this question again. Okay, we need to determine the Thevenin equivalent circuit. So in Thevenin equivalent circuit is a method to simplify the circuit into only two components. The output is still A and B. So what? After we convert it to a Thevenin equivalent circuit, we should arrive at only VTH, which is the Thevenin voltage, and also in series with the resistance. We call the Thevenin resistance, or you can say it's the total resistance of the circuit. And then the output here should remain same as the original A and B here. So that we can connect this one to the external loop later on. Let's say we have external loop later on, called RL loop. If we connect to this terminal A and B, then it's easier for us to calculate the current. Because we have one resistance here, one resistance here, and one voltage here, so it's much easier to calculate instead of this one. If you give your customer this circuit and then ask him to calculate the current, it's difficult, right? You ask him to calculate the current, let's say coming out from A, then now go back to B. So we rather simplify this one to Thevenin circuit like this one. So at the end, after the customer attach the RL, you only have two resistors in series, and then it's much more easier to calculate the current, the output current. Okay, same this one. So what we do here is, first step, we need to calculate the Thevenin voltage. So what I can give you as a good start is, the Thevenin voltage actually is the voltage across VTH. The voltage across A and B actually is a VTH, okay? It's not this one, not this 30 volt, okay? The Thevenin voltage actually is a Vx, okay, Vx here. So what I can tell you is, the first step, as a first step, something for sure that our Thevenin voltage actually equal to Vx, indicated in the circuit. This Vx is not this 30 volt, okay? It's not this 30 volt. Because we still have one resistor here. If without this resistor, then this 30 volt equal to Vx. Because they're common, right? Common node. But since we have this 12 volt in between them, so this Vx has to be, we have to take this into account to determine the Vx. So our next task, of course, is to since here it didn't mention whether to use which KCL or KVL. It didn't mention to use a mass analysis or node analysis. It just say use whatever method you know to find the Thevenin circuit. Okay, this is what we understand. So that the first one, probably we need to use the nodal analysis. In this case, the answer script suggests using the nodal analysis. So for nodal analysis, first we need to define the node voltages. So this being the V1. Another voltages we are interested is here, V2. And the voltage here is the same as V2, right? This is also V2 because they are same node. So here is the ground. So here must be 0 volt here. So at least now you have a clearer picture. If you see all the nodes here, V2, these two nodes are V2, this is V0, 0 volt, V1. So V1 is 30. So far we know that V1 is 30 volt for sure. If you still don't understand this one, nothing I can do already. Because the voltage is between 0 volt and here. So here must be 30 volt, right? Since here is 0 volt already. This 30. So here the potential here must be 30. Because here is 0. Here must be 30. That's why the voltage across is the 30 volt, right? This is what I mean. So if you still do know about this basic, then you need to spend more time. Hold on, let me go and check something. like that. Okay, so the next step is to use the nodal analysis. After I confirm with you these two, use nodal analysis. We learned before, right? Where is it? In question what? The question what is said that you need to use nodal analysis, right? So here nodal analysis is something with using KCL to determine the voltages. So we have 3 voltages here. So if you compare, it's somewhat similar, right? 2 voltages here. Use nodal analysis at node 2 at V2 node. Okay, so you have something minus, according to the question, minus something equal to 0. Okay, at the end, will lead you to the V2, voltage V2. After this, you should be able to find the V2. Okay, and so since V2, Vx is between 0 volt and V2, so V2 is equal to Vx. And then Vx is equal to VTH. So it's you can say it's a quite simple in this manner. So this is your answer. At least you find the VTH already. Because we need to find VTH and RTH, right? So your next task, of course, is to find the RTH. For the RTH, you need to spend another A4 page. Not another A4 page, half a page, okay? The graphic, including the diagram, become a 1 full A4 page. If you remove the diagram, you left only half a page long. So for this one, you need to use also to find RTH, our next task. First, you use nodal analysis again. Since it's appropriate for this circuit, use nodal analysis at node V1. Okay, previously it's node V2, right? Remember? Now you do the nodal analysis at node V1 here, node V1. So I give you the step already. So the equation looks like this: something minus something minus something minus something equal to 0. Because this is KCL, right? Remember, I give you some background information. Nodal is using KCL to find voltages. Mass is to use the KVL to find current. Just remember all these rules. Nodal is to use the KCL to find voltages. So here we use a KCL. Here to find RTH, we use the KCL. This is a KCL, okay? Let's say this is the. Then after you've done all this, then you kind of like replace some of the component. Replace for this current, because it's sum of the current, right? It's sum of the current. So this current you convert to voltage over the resistance. Okay, at the end, you will find that the current. You'll find that the current through the this circuit. Okay, this circuit here. I think I need to copy this circuit again. Okay. This one is quite a bit. It's not complicated, but you need to follow. You need to go through this step eventually. To find the resistance, you need to find the short circuit current. So you take the original circuit here. For the RTH, this is the diagram I mentioned just now. You need to connect something there. Okay. And then you need to find the current I out here. I out. Okay. So from here, I out is here. Okay, I can let you know I out is here. I out is here. And then at the end, you are determine I out equal to some ampere. Here. Okay, and then the last step you need RTH is like this. RTH is equal to the V out over I out. So the V out here, the V out is here. We set to 1 volt. I think we set to 1 volt. And then we divide it by the I, we get the resistance. Okay, let me double confirm again. Sorry. Let me double confirm again. Yeah. So this is the answer. All right. I should, since it's already 7:30, I should immediately cover the remaining 2 questions. Okay. Otherwise, we don't have enough time. So let's talk about this one straight away. 4A, question 4A. Let me close down this one. Okay, now we're talking about question 4A. So this one is opposite to theorem, opposite to Thevenin. It's called Norton. So in Norton analysis, we are more interested in the Norton current, not the Thevenin voltage. We are more interested in the Norton current. Actually, it's the opposite. Actually, what I mean opposite is the reciprocal value. Norton current, sorry, yeah, Norton current and Norton resistance. You pay attention to the resistance. Now is in parallel. This is the Norton resistance. Okay, it's in parallel. And then we have the output voltage here, V out. Yeah. You can treat this one as A and B also, just like previous case. The terminal we connect to output. But compared to the Norton, compare Norton to Thevenin, they are just opposite. One is the voltage and in series. One is the current. One is the current and in parallel. It reminds me of the reciprocal value. For example, R is equal to resistance, right? R is equal to resistance. The opposite of resistance is called a conductance. For example, if R is a measurement of how much you lost, right? Then the conductance is how much you gain. It's totally opposite. So the conductance has a symbol G is equal to 1 over R. G equal to 1 over R, reciprocal value is measuring of the conductance. How good the current can flow. This is how difficult the current can flow. This is how easy the current can flow. You just take the reciprocal value. So this reminds me of the Thevenin and the Norton. They are just opposite each other. One is the voltage, one is the current, one is the series, one is the parallel. Okay, so you can sometimes you can find useful using resistance, sometimes you can find useful just using the conductance to explain the thing. Right? Sometimes people like to use conductance, sometimes people like to use resistance. They are just opposite each other. Okay. So the first step to start actually, okay, the first step here to do the Norton. First, we take away the current source, okay? So the step one, we take away the current source. So step one is to find the short circuit current. Step one, find short circuit current. We replace the output here. We replace the output with a short circuit, just like the previous one. We replace with a 1 volt multiplier. Okay. Here we just replace with the short circuit. Okay. Let me draw the circuit for you. Let me show you how the circuit looks like. Okay, we just remove everything here. Okay, we remove everything here. We replace it with a short circuit. See, we have the power source, we have the current source here. We try to make sure the current flow through this wire because the short circuit current flow through the output. Okay, so this is what we're going to do first step. Is to find the short circuit current. It's a bit new to you probably. So to find the short circuit current, we have the 2 ampere, we have the 2K, we have the 12 volt. Actually, you can use one equation to find, okay, ISC equal to something plus something, okay, something plus something. And then you will find equal to certain milliampere, your answer. You don't need to use any KCL, KVL, okay? You just probably just observe it by observe the circuit. Okay, probably you can use a KCL. Current is going this way, current is going this way, current is going this way. Right? Then you can find ISC. So after you find the ISC, the next step, the ISC is your Norton current actually. ISC is your Norton current. Okay, this IC is actually is your Norton current. Okay. So the remaining step, of course, is to find the remaining step of course is to find the Thevenin Norton resistance, right? Norton resistance. Sorry, yeah, Norton resistance. So the remaining to find Norton resistance, we need to remove the current source, remove the current source, and also remove the voltage source. Okay. And then we join this one with the short circuit. Okay, let me redraw the circuit for you. So this is the procedure we need to do actually to find the Norton value. So what we do here is something like this. We remove this one to find the Norton resistance. We remove this one. We connect a short wire, but we want to measure the short circuit current like previously. And then we also remove the current source. That means we remove all the current and voltage source. Okay, we remove the voltage source here, and then what we left is the 1K. We also remove the other one. So we also remove this one also. Output also remove because the output is not part of the circuit. Okay, the output is the RL. This is the RL. This is RL. So what we left is something like this. Okay, what we left something. I think the question didn't explain it enough. That the R2 ohm 2K ohm here actually is the RL. Remember, I talked about it earlier on. I say that eventually the Norton circuit going to connect to the external loop, right? Connect to one external loop. Remember, I brought this one in the previous table. I say this one will connect to RL. Eventually, right? This is the customer resistance, right? In this case, the RL here is already been put inside here, but the question didn't mention it actually. The question just asks you to find a Norton without mentioning that this 2K actually is the RL. It's not part of the original circuit. Okay, we need to convert the original circuit here into these two components, and then at the end we leave the RL here to calculate the Vout. This is what I mean. Like the Thevenin, if you refer to the Thevenin again, I say that we convert. Here's without the RL, right? Here's without the RL, A, B. So we convert this one everything here into two components. Then we attach the output to the terminal AB. Then we calculate the current, right? So this Thevenin is calculate current, right? Calculate output current. Then Norton is to attach the output here to calculate the voltage, output voltage. That's why they use the Norton theorem to find these two values. Then at the end we can find the output voltage. Okay. So now to find the RTH, I already mentioned this is a circuit after we remove the current source, voltage source, and RL should not be there in the first place. This is a circuit to find the RTH. To find RTH, so this is a circuit. Okay. So you need to find the total resistance here, RTH, Rn, total resistance here. After you find it, then at the end, you end up as the Norton circuit, Norton current from the previous slide here. Norton current is IC. You have the Norton current, you have the Norton resistance, Rn, and then you have the customer load 2K. Then you find the V out here. Okay, you find the V out. So to find this V out, you need to know this value, because V equal to IR, right? I times R. V, the voltage here equal to the current multiplied by the resistance. So we have two resistance here. So you need to parallel first. You need to parallel this resistance. After you know the Rn from here, you parallel these two, and then you just use this equation. V out equal to something. Right? This is Ohm's law. Okay. Now we are down to the last question, right? The last question here. So we have got about 50 minutes. Right. Okay. Let's take 5 minutes off. Then this question should be easy. Don't worry. I remember this question is just follow some step. I give you the step and then you do the rest. Okay. So let's take a break first. 5 minutes. All right, let's finish up the last question. Basically, what we need to do here is using the superposition theorem. Okay, let me tell you what is superposition theorem. You can see it here, the Vx indicated here, okay, is what we want to find to determine the voltage across 4 ohm. The voltage across 4 ohm is a Vx, okay. In this circuit, we have 3 independent sources, 1 12 volt, 3 amp, and 20 volt. Okay, so what the superposition means that for each case we only turn on one source only. Okay, let's say we turn on this, we turn off these two. We have the first Vx. Vx1 is based on only 12 volt. Remove these two, the other sources, and then we plus another Vx2 at the same position here. We just turn on this one, remove the other two. This time we turn on 3 amp, remove 20 volt and 12 volt, and then we find Vx2. And then the last step is that we find a Vx3 by turning on the last one, remove this one. And then if you sum all these voltage together, it's equal to Vx actually. That means we turn on one source at a time, and then we sum all the output to get the final Vx. Because final Vx, it consists of three independent sources. So by using superposition theorem, we find one at a time, based on one source at a time. That means we only turn on one source at a time to find the 3 independent voltage source. At the end, we sum 3 of them to find the final value. Okay, so the first step is to turn on. Okay, let me write down here. Step 1, turn on 12 volt. Okay, turn off 3 amp and 20 volt. Okay, when you turn off 3 amp, it becomes open circuit. Okay, open circuit. Open. When you turn off 20 volt, replace with the short circuit. Replace with the short wire. Okay, short wire. Short. Can you understand or not? What we mean by turn off is you turn off this one, you totally make it an open circuit here. But you turn off this one, you need to replace with the short wire. Okay. Then you do the KCL at not V1. Let's name the V1 here and V2 here. You do the KCL at node 1. KCL is to find the current, right? KCL is to find the voltage, right? So do the KCL at V1, KCL at node V2. You do the KCL at node V1, okay? You will get one equation. You will get something minus something equal to 34. Okay, I give you part answer, right? And then you do the KCL at node 2, node V2. You will get something like something minus something equal to 0. So you have now you have 2 equations. Now you have 2 equations with you. It's not 0, right? This is something plus something, right? It's not 0, okay? This is 0, sorry. This is 0. This is not 0. So let me make clear to you, otherwise you'll confuse yourself. Let me redo it. Okay. Something equal to 0, okay? 0. This is not 0, right? This is not 0, this is 0, okay? This is the position number 2, position number 1. And then inside this equation, we have the Vx1. Inside this equation, we also have Vx1. And then after you solve for the unknown, you will find that the Vx1 is equal to the first value you find. After you've done these two steps, you'll find the first Vx value. It's by turning on 12 volt, turning off 3N and 2N. So remember, 3N, when you remove, you can just remove it, leave it open. But 20 volt, you need to connect a short wire. You cannot make this here open circuit. If you make here open circuit, then this 2 ohm become irrelevant only. So you need to replace, take away 20 volt, replace with the short wire here. Take away this one. And then you calculate the Vx of this one, between it. So the next step, of course, the next step, step number 2, is to remove the next. Remove 12 volt and 20 volt. Okay, keep 3M. So when you remove the 12 volt and 20 volt, you need to replace with a short wire, right? Replace with a short wire. When you remove the voltage, you need to replace with a short wire. Short. Okay. After that, there's another node here called the node C, V3. So you use the KCL at node V3. Okay. And then you should be able to find, you should first appear something like this, something plus something plus something equal to 3. At the end, you will get Vx2. Of course, inside here is a Vx2, Vx2. Inside got Vx2, okay? But this is not Vx2. Inside, you can find Vx2. Inside here, this part, okay? Also here, also can find Vx2. At the end, you have Vx2 equal to some number, okay? So you complete the second task already. Now you're down to the last one. Step number 3 is to remove 12 volt and 3M. Keep 20 volt. That means we keep the last one. We keep the last voltage. We remove this one, okay? So again, if the rules apply, this one replace with the short wire. This one, keep it open circuit. Okay. Then after that, you apply KCL at node V4. So where is node V4 actually? Where is the node V4? V3 is here. I mean V4 is here. Hold on, let me double confirm it. Let me double confirm. You need about 3 pages long, I think. The last question is easy, but it takes so many steps. No, no, it's wrong already. So here, V4 is here, so here. V2, V2, V2. So it should be V2, okay? So it is V2. There's no V4, V2, right? After that, you should arrive at the Vx3 over something plus Vx3 over something plus Vx3 minus something over something equal to 0. So this is the equation for the KCL at V2. And then at the end, you find Vx3 equal to something. Because it's one unknown only, Vx3. So therefore, at last, Vx equal to Vx1 plus Vx2 plus Vx3. Is the final answer. That's it. So that's all for this assignment 1. So please complete it. Okay, complete. Let me write the last message here. Complete and submit. Okay, it by 11 February. 11 February, I remember, is the Sunday. Is it 11? Let's go back to the notes again. Yeah, 11. Okay. Before the end of Sunday, you need to submit it. Okay. I hope I should remind you if I can remember. I should remind you with a few days before this happened. I should remind you. Okay, that's all for today. I'll save and then share with you the T2 classwork. I'll share with you the WhatsApp. Because we're 3 students, so let's share in WhatsApp. Okay, I'll share with you later. Never mind, I'll put another copy here. I put one copy here also. Here, inside this T2 here, inside this file tag. I'll share the file here also. All right. Okay, that's it.